I'm Dr. Jeremiah Tidey. I work at the X-ray Research Technology Platform as a research technical professional. I'm an X-ray crystallographer. I study the arrangement, interactions of atoms and molecules and crystals. And very recently we got a new electron diffractometer. So I'm now charged with working on that and developing that new field. I always thought interesting chemistry happened in solutions. You see reactions take place, God, that's really cool. But then in my master's, I did a project in high pressure crystallography. I found it really exciting, really very satisfying seeing how molecules actually packed and interacted in crystals and started to learn, there's real chemistry here. If you imagine a disco ball, right? Shine a big beam of light at it, you get reflections everywhere, lots of beams of light. If you were to track where all of those went, you could do some maths to reconstruct the disco ball. This is actually a pretty good analogy for what I do with crystals, and if you shine a beam of light, crystal, or radiation, X-rays, neutrons, electrons, it scatters and beams go everywhere, different intensities and different spatial arrangement that is unique to that crystal. And by clever maths using a computer, you can reconstruct the building block, the brick of the crystal, i.e. the way the atoms and the molecules pack. And then from that, we can draw a lot of information about the chemistry inside the crystal. So that's what I do, both locally and as part of the National Electron Diffraction Facility for academics and industry all over the UK. And we are engaged with research networks across Europe in bringing this technique forward, not just advancing the technique, but advancing science as part of it. Pretty much everything we make is crystalline, unless it's made of glass or wood or plastic. And to study crystals in this manner with the single crystal disco ball approach, you'd need a crystal of, say, a few tens of microns in size. And that's great if you can grow crystals like that. If you can't, you'd go to what we call a synchrotron, and this would let you study crystals down to, say, 0.001 millimeters, like a micron or two in size. But any smaller than that, and you can no longer use this single crystal approach. And that's where electrons come in. So electrons interact with matter thousands of times more strongly than do X-rays. So you can now study crystals thousands of times smaller, right down to the point where it's a few nanometers in size and it's no longer really a crystal anymore, and you're talking about a few molecules. So this is going to be a game changer. If we want to advance our materials, advance our chemistry, we need to know what structures they are. And where previously this, for a lot of stuff, wasn't possible, is now possible. An area for which we're finding electron diffraction to be really useful is in the study of MOFs. These are metal organic frameworks that are being looked at for a lot of environmental purposes. Similarly, also battery technology. So these are crystalline materials, but have often very poor crystallinity. And obviously, as you think, we try to move to environmental friendliness, to scrubbing the atmosphere of CO2 or cleaning our off gases and flue gases, and relying more on solar power, on batteries. That's two big areas in which we are starting to find electron diffraction really useful for. And so this positions Warwick right at the forefront of this revolution in structural science. And together with the University of Southampton and our partnership as the National Electron Diffraction Facility, we're really spearheading the advance and development of this technique across UK science.